Hello, in this video we're going to talk about linear transformations and matrices, and in the next video we're going to also talk about how linear transformations are related to matrices in more specificity. So all vector spaces in this section are going to be subspaces of Rn. So whenever I say something is a vector space, it means it's a subspace of Rn for some n. So here is the definition of a linear transformation, and then I'll explain, I'll give you a few examples and I'll explain what that actually means. Let V and W be two vector spaces, which means V is a subspace of Rm and W is a subspace of Rn for some positive integers m and n, and they don't necessarily have to be the same integers. A function L from V to W is said to be linear or a linear transformation if for every v and w, for every two vectors in the domain, L of v plus w is L of v plus L of w, and for every scalar c, L of cv is equal to cl of v. So what does this mean? It means it basically preserves the structure of the vector space. So it preserves the addition and it also preserves the scalar multiplication. So now let's look at some examples to get a better sense of what these functions are, and throughout this section you'll figure out why these functions are in fact important. So here are several examples. So the first one is f of x equals c times x, where c is a constant from R to R, is a linear transformation. So what do we do? We have to check those two conditions, additivity. So let x and y be vectors in the domain, in this case it's just R, and c be a scalar. So I think of x and y as, or let's call this one maybe c1, x and y as like vectors, and c1 is a scalar. Now we'll evaluate f of x plus y. F of x plus y by definition is c times x plus y, which is cx plus cy, and of course cx is f of x and cy is f of y. Now we're going to evaluate f of c1x. F of c1x would be c c1x, which is c1 cx, which is c1 f of x. So that's the first one. So that means it satisfies both additivity and homogeneity. So we had these two conditions, additivity and homogeneity, and since it satisfies additivity and homogeneity, it is linear. In fact, I'm going to actually make that argument. So by definition, f is linear. Next one is f of x comma y equals 2x plus 3y. So I'm going to do basically the same thing. So let start from two vectors x1 y1 and x2 y2 in R2 in the domain. Oh, and by the way, this would have to be R2. There's a typo here. And we're going to also take a scalar inside R. We are going to evaluate g of x1 plus x1 comma y1 plus x2 comma y2, and we are also going to evaluate g of x1 comma y1 plus g of x2 comma y2, and then we'll have to show that those two are in fact the same. If they are the same, then we know that it would be linear and it would be additive, and then we'll have to check the homogeneity. And if not, then we would know that it is not linear. Okay, so this is equal to g of, by addition of two vectors, this is x1 plus x2 comma y1 plus y2. This is how we add vectors in R2. Now by definition of g, this is twice the first component plus 3 times the second component. So twice the first component plus 3 times the second component. If we distribute 2 and 3 here, we get 2x1 plus 2x2 plus 3y1 plus 3y2. Now if you look at these two give us f of, or in fact g of, x1 comma y1, and the other two, this term and this term, give us g of x2 comma y2, which means g is additive. Now we'll look at g of c times x1 comma y1. This is g of, by definition of scalar multiplication, this is cx1 comma cy1. Again, by definition of g, that's twice the first component plus 3 times the second component. Now, we can factor a c. We get c times 2x1 plus 3y1, which would be c times g of x1 comma y1. So that means, by definition, g is in fact linear. Okay, so the first two functions that we looked at are in fact linear. Okay, so let's look at the third function. H from R to R, h of x equals 2x plus 3. So let's look at the conditions again. So let x and y be in the domain and c be a scalar. So technically you could just say x, y, and c are in real numbers, but I write it down this way to kind of be a little bit more clear. So let's evaluate h of x plus y. H of x plus y is if you look at the definition, it was twice the input plus 3. If you go back and look at what we had, it's 2x plus 3, so it's twice that plus 3, which is 2x plus 2y plus 3. But if you look at h of x plus h of y, that becomes 2x plus 3 plus 2y plus 3. And this is 2x plus 2y plus 6. So in fact, the equality never happens. So in order for it to be not linear, it doesn't have to be that the equality never happens. It just has to be the case that the equality does not happen for some x and y. So, but in this case, h of x plus y is never the same as h of x plus h of y, which means h is not linear. So keep in mind that in order to show something is linear, you'll have to show the equalities, additivity, and homogeneity hold for every two vectors and a scalar. In order to show something is not linear, you'll have to just give one example. So another way of doing that, and maybe a faster way, would be to do this. Say h of 0 is 3. h of 0 plus 0 is 3. h of 0 plus h of 0 is 6, and these two are not the same. This is an alternate solution to the same problem. Therefore, it is linear. So if you know, you basically have a sense of the fact that it's not linear, all you need to do is to just give this example. Finally, the last condition is, the last example is a function from Rn to R defined by inner product. So W is a fixed vector, and we take the inner product of W with a vector V. So we're going to do the same thing. So let U and V be in Rn and C be a scalar. So we're going to look at K of U plus W plus V. That's the inner product of W and U plus V. Now we're going to use linearity with respect to the second vector. We get WU plus WV. And this is K of U plus K of V. So K does satisfy additivity. Now we're going to do K of CU. This is W comma CU, which is, again, by linearity, we can take the C out, WU, and this is C times K of U. So therefore, K is in fact linear. So from these four functions, 3 of them were linear and 1 was not linear. Okay. So now that we are done with these examples, let's look at a very useful theorem. And I'm going to go over the proof of this theorem. So what is the theorem? If you look at the definition of linearity required us to check two different things. First, additivity. If I go back and take a look at the definition. First, additivity, and second, homogeneity. Now, you can in fact combine the two into one thing. So, and that brings me to the theorem here. So let L from V to W be a function between vector spaces. Then the following are equivalent. So for those of you who may not be familiar with exactly what equivalent means, it means if one of these three things happen, then the other two also happen. So if L is linear, then you have B and you have C. If B is valid, then C and 3 are true. If for a function L, B is true, then C and A are also true. And for a function L, C is true, then A and B are also true. The way you want to prove equivalencies of a bunch of statements is by doing a cyclic argument. So what does that mean? It means by proving that A implies B, you want to create a cycle here. B implies C and C implies A. So that way, if you know A is true, then B would be true, and therefore C would be true. So A implies both B and C. So you don't need to necessarily go over all 6 different implications. You don't need to go A implies B, B implies A implies C, C implies A, C implies B, B implies C. So there are 6 implications you'll have to prove. But if you only prove these 3 of them, the others follow. Okay, so we'll go over that. And oftentimes one of these cycles is easier than the others. So let's just start with A. So A implies B. So this is what we're going to do. So suppose L is linear. So since L is linear, L of U plus CV is equal to L of U plus L of CV. And this one comes from additivity. And that's equal to L of U plus CL of V. And this one comes from homogeneity. So we showed that if L is linear, then it would also satisfy B. And I will tell you why we need this theorem and how it would help. B implies C. So suppose we have B. So what does that mean? It means if I take L of AU plus BV, I can write this down as L of AU plus BL of V. This is by the by part B. I can just take this one as one vector and then take this one as another vector and then take the B out. Now I would like to take the A out. So how would I take the A out? Here's how I can do that. I can write down L of AU as L of 0 plus AU, and I can write this one down as L of 0 plus AL of U. So that way I can actually take the A out. But why is it that L of 0 is 0? I also need to show L of 0 is 0. So here's how we can do that. L of 0 is the same as L of 0 plus 1 times 0. And I'm going to use part B. I'll write it down as L of 0 plus 1 times L of 0. Now these two can be cancelled, and that gives me L of 0 is in fact equal to 0. Now that L of 0 is 0, that means L of AU is equal to A L of U. This is because of this equality. So I can replace L of 0 by 0, and that would give me L of AU equals A L of U, which means L of AU plus BV is A L of U plus B L of V, which is exactly what we wanted. So that means B also implies C. Now we'll have to show that if C is satisfied, then A is also satisfied. So let's assume that something satisfies C, and we'll have to show, in fact, L is linear. So if you look at L of, so it's AU, I'm going to replace A by 1, and BV, so I'm going to replace B by 1 as well. This is 1 L of U plus 1 L of V. And what does that mean? It means L of U plus V is equal to L of U plus L of V, which means L is additive. So that's nice. Now we'll have to take L of CU, and I'll have to show that this is CL of U. So I'm going to write it down this way. This is L of 0 times 0 plus C times U. and I'm going to take the 0 and the c out by part c, and that's obviously just c L of u, which means L is also homogeneous, and that tells you that L is linear. Okay, so L is homogeneous, therefore L is linear. Now let's talk about when to use this theorem. Okay, let's look at this theorem and see when to use this one. So here is when we would use this theorem. If you want to show something is linear, you either use the definition or use part B. Oftentimes part B would be a bit shorter. If your problem doesn't get too complicated, then I would just use part B in order to show L is linear. So that's what you want to do with this theorem. If you know L is linear, so let me actually write it down. So to show L is linear, either use the definition or part B of the theorem above. This is oftentimes the best way of showing something is linear, using part B. If you know something is linear, then this part C is the strongest one, because part C allows you to take out all these different constants. So if we know L is linear, then C is the most useful one, because it allows you to take different constants out. Okay, let's actually see that in an example. So we are going to find all linear transformations from Rn to R. So let's write down a x1 through xn. So let's just start with that. So let me start with a notation here. So let x1 through xn be in Rn. I would like to find f of x1 through xn. Okay, so because I would like to use linearity, I'm going to write down this vector x1 through xn as a linear combination of some vectors. So the most natural thing to do would be to write it down as a linear combination of e1 through en. So this is x1 e1 plus xn en. Now, if you use part C of the theorem that we had up there, you could just basically take out all these constants and write it down as a sum. So you could write it down as x1, and this is something you can do by induction. So part C of the theorem was for only 2 variables, but you could do it for n variables by induction. And this is one of the examples in the notes. So x1 f of e1 plus xn f of en. Now, this is interesting because this is exactly the dot product. If you look at the vector x1 through xn and look at this vector that the components are f of e1 through f of en, this is exactly the dot product of these two vectors. So what does that mean? It means f of e1 all the way to f of en dotted with x1 through xn gives us this function. So in other words, f of v is equal to w dotted with v, where w is a fixed vector. W is f of e1. It doesn't depend on the input. It of course depends on the function. It doesn't depend on the input. And this is for all v. Let me explain this. So if you look at this input and call the input v, so this input is v, then here you have the exact same vector v here, and this is a fixed vector. This does not depend on the input. This is, if I call this one w, that would be w dotted with v. Okay, so every linear function would look like this. Now, this is not enough because I would also need to show that every function of this form is linear. So furthermore, every function f from Rn to R given by f of v equals w dotted with v is linear. Well, why is that linear? This is the example that we just did. By example, let's go back and take a look. In fact, the example that we did was for every inner product, the function k in this example, example 4.2 part D. So by that example, in fact, this is linear. So what we showed was, if you have something that is linear, it would have to be of this form. And if you take anything function of this form, it is linear. Therefore, every function that is linear from Rn to R would have to be a dot product with a fixed vector. So that's a very interesting relation between the things that we have learned before, the inner product, and this new concept of linearity. Okay, so that's nice. So now let's look at another example. Okay, so what we want to do in the next example is to find all linear transformations from R3 to R2. So here is how we're going to do that. So we're going to do something similar to what we did above. So let's start from x1, x2, x3 in R3. And let's write down f of x1, x2, x3 as f of x1 e1, so similar to what we did before, x2 e2, x3 e3. And e1, e2, e3 are just those standard vectors, standard bases of R3 in this case. Now we're going to write that down using the theorem, using part C of that theorem as a linear combination. So it would be x1 f of e1 plus x2 f of e2 plus x3 f of e3. It's very tempting to say that this is a dot product, but it's not quite a dot product, because if you recall, the codomain here is in fact R2. So these are in R2, not R. If these were real numbers, then this would be a dot product, but this is not a real number. These are vectors. But if you take a look at the coordinates of these, the coordinates are real numbers. So let's just say the coordinate of the first one is a1, b1. The coordinates of the second one are a2, b2. Coordinates of the third one are a3, b3. Then you can say, in fact, the coordinates are x1, a1 plus x2, a2 plus x3, a3, and x1, b1 plus x2, b2 plus x3, b3. And these two are dot products. The first one is dot product of x1, x2, x3 and a1, a2, a3. And the second one is the dot product of x1, x2, x3 and b1, b2, b3. So this is really interesting. So what I got is this, f of v, and this was our input. The vector x1, x2, x3 was our input. So this is our v, is equal to v dotted with some vector, I'll call that w1, and then v dotted with another vector w2. So this one is w1 and this one is w2, and the input was the vector v. Now it's really interesting because we got kind of similar to what we had before. So both of the components are going to be dot products. So if f is linear, then f looks like this. Now I will have to show that everything of this form is also linear. So this is for some fixed x1, v1 and v2. I'm sorry, w1 and w2. And w1 and w2 are in R3, of course, because the domain is R3. So now, if you look at this, this is in fact linear. So every function of the form, I'm going to call this a star. Star is in fact linear. Why? Because if I take two vectors, and this is again not very difficult to see, I'm going to show that using the theorem. So let x and y be in R3 and c be a real number. So and I believe I called it f, so I'm going to keep calling it f. So I'm going to evaluate f of x plus cy. I'm using the theorem, the part B of the theorem. F of x plus cy. This is going to be, so by definition it's x plus cy dotted with w1 comma x plus cy dotted with w2. Now I'm going to use linearity of dot product because I know dot product is a form of inner product which is linear. So this would be x dotted with w1 plus c y dotted with w1 comma x dotted with w2 plus c y dotted with w2, which is equal to x dotted with w1. I'm going to break this up into two different vectors, comma x dotted with w2 plus c y dotted with w1 comma y dotted with w2. This is equal to, okay, so the first one is just f of x and the second one is just cf of y. So this means f is in fact linear. So that's the way really you want to show something is linear. It's a better way of showing it's linear than using the additivity and homogeneity. It's a little bit faster if you don't get confused by combining the two, because the variables get more and it might be a little bit more confusing. Okay, so this is very interesting. Every linear transformation comes from dot products. Dot products have with different vectors in different components. So now if you look at the first example that I did, the first example that I did was if I take a function from R to R, f from R to R, and I look at that as f of x equals cx, this is linear. So in fact, it's interesting to think about all linear transformations from Rn to Rm as things of this sort. So this is the objective here. Now, and that's like one of the things we're going to talk about it later. So here is now what I proved. Proved that all linear transformations from Rn to Rm are given by this, where w1 through wm are vectors in Rn. I proved this one not quite in the general case. I proved it for n equals 3 and m equals 2. So the proof in general is actually quite similar. So we'll go over the proof of this one. So suppose f from Rn to Rm is linear. So let's write it down and see what we get. So we're going to write down an input x1 through xn as a linear combination of e1 through en. So f of x1 through xn is going to be f of, I'm going to use sigma notation, makes things easier, more compact, j equals 1 to n. Now I'm going to use linearity here. This would be the sum xj f of ej. This is like the third part of the theorem along with induction. And as I said, this is one of the examples in the notes. Now, this is essentially a bunch of dot products. So if you call f of ej as, so I'm going to call these some vectors. So let's say f of ej, and I want to kind of match these. So these are going to be our w's. They're going to give us like the w's. Okay, so I'm going to call f of ej as a j1, so that's the first component, a j2 all the way to a j, and I know that f of ej is in Rm, so it would be jm. Okay, yeah, so these are our vectors, and of course this is in Rm as I just mentioned. Okay, so now I'm going to take that and plug it into the sum. So f of x1 through xn becomes the sum xj, and then the components are aj1 all the way to ajm, and this j goes from 1 to n. Now if I combine the coordinates, so the first coordinate becomes the sum xj aj1 j equals 1 to n. The second coordinate is the sum xj aj2 j equals 1 to n, etc. And the last one is the sum xj ajm j equals 1 to n. Okay, so now if you look at these vectors, the first one, these components, the first one is the dot product. The first one is the dot product of x1 through xn and some vector. What's that vector? It is a11 all the way to an1, etc. And the last one is x1 through xn dotted with the vector a1m all the way to anm. So if you call this one v, which is the input, and call this one w1 and this one wm, what we end up getting is f of v is equal to v dotted with w1, that's the first component, and every component is a dot product. V dotted with wm for fixed vectors w1 through wm inside Rn. Okay, now the way I wrote it down was as a column. I wrote it down as columns, but it doesn't really matter. So I just showed that every linear transformation would have to be coordinates would have to be dot products, and then this is also linear because dot products are linear. So I basically went over that for the case of 2 and 3, from R3 to R2, and it would be similar. So similar to above, we may show f is linear. Okay, so every linear transformation from Rm to Rn would be dot products with certain vectors. Okay, so that brings me to the next definition. As I mentioned earlier, every function from R to R that is linear is a multiplication, on the left. And these are in fact everything. And the reason is it's a dot product, and the dot product is just multiplication. Now we can think about that as also a multiplication. So in fact, this is the way we're going to define multiplication. So given an m by n matrix A, where wj's are rows of A, and given a column vector v, the product of A and v denoted by AV is defined by AV is w1 dotted with v all the way to wm dotted with v. So this is how we define matrix multiplication. This is one reason that matrix multiplication is defined in a kind of a weird way. So next time we'll talk more about these matrix multiplications and their relations with linear transformations. So I will see you in the next video.